So we just saw that white noise is nothing but a Gaussian probability distribution. And actually we can generate brown noise from the white noise. If we simply integrate the white noise, it results in the brown noise. So this is what this formula is saying here. So earlier we had seen this expression, which is that of the white noise. If we just simply integrate this function, then what we get is the brown noise. And in Python, this is exactly what we are going to implement. We are going to do the integration of the white noise. And this is how it looks. As we all know that integration action leads to a low pass filtering action. So now you can see that this noise is having some very low frequency fluctuations. And in fact, it's just going randomly in some direction. That's why it's called a random walk. So let's implement this brown noise in Python environment. So in the previous section, we had generated this white noise. And now our job is to generate the brown noise. So what I'm going to do is I'm going to take this white noise and insert in a function called compsum, which is nothing but integration. So I use this function from NumPy library called cumulative sum and insert white noise inside it, and that's what is going to generate the brown noise. Rest everything is the same as what we saw earlier in the case of white noise. So this is time axis that I'm generating, and then I'm plotting brown noise in time domain. So this is the plot between time axis and the brown noise. So let's see how it looks. So this is exactly how the brown noise looks. This was the white noise, and we just took it and integrated it. So you see here it's fluctuating so randomly. It has got some very high frequency components. But when we integrate it, those very randomly wild swings of this signal, they get low pass filtered. And as a result, you see that the signal is now exhibiting very low frequency components. And this is what is called random walk. So every time I run this, we are going to get a different waveform, because now this time it is going up. But still, you can see that the frequency components are of very low. Like here, it is just rising. And in fact, there's one very interesting property of this signal. It is a non-stationary signal. What I mean by non-stationary is that the statistical properties of this signal are no longer constant. For example, when we talked about white Gaussian noise, it's a stationary noise, which means the mean remains constant. So it started with 0, and all throughout the duration of the signal is fluctuating around its means, which means the mean is constant. It's not changing. And also the standard deviation is not deviating far too much. It is constant. The fluctuations inside this noise are almost of the constant amplitude. But when we see this signal, it starts off from 0, and actually if we draw a mean line, it will go somewhere like this, which means that the mean of this signal itself is changing, and that's the classic definition of a non-stationary statistical noise. Or not only its mean is changing, if you see the variance or the standard deviation of this signal is also getting changed. So here we have some variance, some fluctuation, and here we just have a straight line, no fluctuations here, which means the standard deviation has gone to 0. It's just the mean which is shifting now. And then we have mean becoming almost constant here, and then some standard deviation happening. And thereafter again, the signal mean is rising up. So that's how a non-stationary signal looks. And these kind of signals, they are problematic signals. They cannot be handled through linear filtering theory. Linear filters, they are very good at handling white noise, but they are not so good at handling such kind of signals like the brown noise. And for that reason, we have statistical filters like least mean squares or recursive least squares. Normal filters like sliding window or sliding median or FIR, IAR kind of filters are very poor in handling such kind of a noise. So the next step is that we are going to listen to how these how these noises sound. For that, let me just switch over to the speakers that I have on my desktop. And essentially, I've taken this white noise time series, and I have used the audio function of IPython, and I have specified the sampling rate of my sound card, which is 41.1 kilohertz, and converted these samples into a wave file. So let's listen to white noise. So as you can see, it has no preference for any frequency. Lower frequencies are also amplified, higher frequencies are amplified. This you'll be able to notice in a much better manner when we play the brown noise. So again, I'm using the audio function to export this brown noise file samples and converting it to a wave file. So as you can see, once we filter out the high frequency component, the noise become more like a hum rather than a hiss. Let's just play it again. Just listen to this white noise. This is more hissy. It is more shrill in comparison to the brown noise. Let's play the brown noise now, which is the low pass filtered version of the white noise. So it's clear that what is the impact of low filtering the white noise. The signal becomes something like this. Please note that this amplitude is fluctuating very wildly here, and we'll have to deal with this problem. That's the reason why random walk is a very difficult signal to handle. Moving further, so we have done analysis of these signal in time domain. Let's look at them, how they behave in frequency domain. So in this particular code, I have just taken the white noise and I have just I've done the FFT operation on that and calculated the white noise spectrum. Then for the brown noise, I have taken the brown noise time series and did a FFT on top of it and calculated the brown noise spectrum. And then I'm going to generate a frequency axis and do plotting of these two noises and see how they look in frequency domain. So there we are. Now here the x-axis was time, but now we have converted to frequency spectrum. So here we have a frequency. As I said that I'm generating frequency up to 44.1 kilohertz. So the Nyquist frequency is somewhere around 22. I'm taking only the Nyquist component of the frequencies. And what you can see here is this y-axis is power axis. So white noise has no preference for any frequency. The power is equally distributed across the spectrum. And that's the reason why we have low frequency as well as high frequencies as well as midtones in the sound file that we just played. On the contrary, when we look at the brown noise has got very high power spectrum for lower frequencies, and as the frequencies go above 250 hertz, they get attenuated. As a result, all these high frequency components have very low power, and that's the reason why instead of you hearing a hissing sound, you hear a humming kind of sound from this particular signal. So in the next section, we will understand how we are going to generate the other kind of noises and then come back to Python environment and implement them.